Okay, in this video, the last one for this week, I'm going to introduce some of the basic terminology associated with studying internal combustion engines. This is going to come from sections 9.1 through 9.4 in your book. And basically the idea is that an internal combustion engine is going to, first of all, happen in pistons and cylinders. So these are going to be modeled as closed processes. Now I know that gasoline and air are flowing in and out throughout the process, but because the really significant steps of the work are going to happen in a piston cylinder, it's best to analyze them as if they were a closed system. That means that the form of the first law is Q equals W plus specific internal energy at state 2 minus state 1, kinetic energy at 2 minus 1, and potential energy at states 2 and 1. Now usually kinetic and potential energy can be ignored, so the form is probably best considered to be Q equals W plus U2 minus U1. So that's going to be the basic thing that we're going to be needing to analyze. But when we talk about car engines in particular, there's a lot of other vocabulary that we use. And so some of these words you will have seen and heard before, maybe not known exactly what they were. Some may be new to you. But when we talk about the displacement, it's the difference between the maximum size that is inside this piston cylinder minus the minimum. And since car engines actually have several different piston cylinders, we're going to take the number of cylinders times the maximum minus minimum to get the total volume of displacement. We also sometimes talk about a compression ratio. Depending on what you look at, sometimes CR is one form I've seen, R sub V. It is a volume ratio. As we do this compression, it's the ratio of the maximum to the minimum. So displacement is the difference between them. Compression ratio is the ratio between them. And both of these are nice ways to describe the engine geometry. Now, a couple of other things, ways that we talk about the amount of power and work. One is the mean effective pressure, or MEP. MEP is the net work divided by the displacement volume. And so it's going to be the average pressure over the cycle. If I'm using specific net work, I can just look at one cylinder perhaps and have an understanding of what's going on in the cycle. But if I'm going to look at the total engine, total work, total displacement volume, consider all the cylinders. The work ratio is the net work over the positive work, and it's really, as much as anything, telling me how sensitive the cycle is to the irreversibilities that ultimately happen inside my cycles. And then power. We all know that power is really what we're looking for when we buy a car engine. But ways I can calculate this. So we don't really talk about flow rate times work. That's what we would have done in the old days. Take specific work multiplied by a mass flow rate. But that doesn't really make sense anymore because I've got multiple cylinders and just all sorts of things going on. How fast are they moving the material in and out of the cylinder? And so various ways I can calculate that. One is, okay, alpha is just a parameter. For a four-stroke engine, it's 1/2. For a two-stroke engine, such as what you would find in, I would say, a lawnmower, okay, then you would use 1 for alpha. But multiply this by the number of cylinders times the mass. It's not the mass of the material inside the cylinder, okay. Net work times the speed over 60, since RPM, we want it in 60 so we can get it into seconds. Alpha times the MEP, okay, the mean effective pressure, times the displacement volume times RPM over 60 is another way, depending on what you've calculated. Now, frequently we're going to be asked to calculate the MEP, and displacement volume is something that we typically know about an engine, so this latter definition is typically the one that's more useful. We also, of course, are going to want to be able to compare engines, which one's bigger. And of course, one thing that you want, if you're buying a car, maybe you want to know, I want the most powerful engine. And so that's a simple thing to look at. But also we want to know about how these work to conserve fuel, to make good use of resources, etc. And so various things we can look at. If we compare thermal efficiencies, that's a ratio that is telling me what my cycle work is to heat transfer input, how much fuel it's using. If I look and compare from one car to another or from one engine to another, the comparison of these is basically indicating how it converts the fuel to power. Okay, so a larger thermal efficiency would be a good thing to minimize fuel cost. If I want to look at the MEP, if I have two engines with the same volume, same displacement volume, then the one with the larger MEP is going to produce more power. Okay, and then that work ratio. The reason I'm looking at the work ratio is I want to know whether or not friction is going to really make a lot of difference. Okay, the closer the work ratio is to 1, the less the engine cycle is going to be affected by irreversibilities. Car engines are very strongly irreversible. We are going to model them as reversible. We're going to make a lot of assumptions as we do the models in the next few days, but we're going to need to have some ways of simplifying those. Before you come to class, I really wish that you would take a look at a couple of videos. These are some I like. There are many, many available on the web, but these are some with some animation that I think will help you understand what the differences are between how an Otto cycle works, which is supposed to be a model of how a basic spark ignition engine works. And then I have these that are how a diesel cycle works, okay, which is a compression ignition engine. So a diesel engine is going to work a little bit differently. And I think these two animation videos for the different cycles will give you a little bit of an understanding of what is going on inside the engine. So as we look at our models, we can see the simplifications that we're needing to make and see whether or not it seems rational and reasonable. And then we'll also be looking at the dual cycle, which actually is an improvement over either one of these in terms of the ability to actually model what happens in a car engine. So this concludes the video portion for the week, and we will see you in class.